Hey, thank you for having me today on the Wide Bandgap day of the PowerUp Expo. And today I will discuss with you the challenges that I see in the power semiconductor market for the coming decades, and also how Nexperia is planning to contribute to address those challenges. And also specifically, I'll tell something about the Nexperia GaN solution and how that fits in addressing the challenges, including an insight on application, technology, and also packaging. First, I'll give you the background of Nexperia, then elaborate on the challenge that we have jointly ahead, address the technology landscape, talk specifically about the Nexperia Power GaN, and then do a short wrap-up at the end. Let me first give you a brief overview of Nexperia's business highlights. And I think it's also fair to share my company context at the beginning of this presentation, so you also understand my perspective into this matter. Some key facts around Nexperia. We are experts in cost-effective production of discrete MOSFET components, analog and logic ICs, which we often refer to as essential semiconductors. Last year, 1.4 billion revenue in 2021. It's not a big secret, but it will be significantly above. Market share a bit over 8%. And we produce more than 100 billion units on an annual basis. And just for reference, that's roughly 1/10 of the global semiconductor volume. We have 3 owned front-end and 3 owned back-end sites. And we're working in parallel to that with long-term foundry and subcon partners. So all in all, 60 years of experience in semiconductors, legacy in Philips and NXP, and since 2017 standing on our own feet. So far about Nexperia. Let's now look at the challenge that we have in front of us. As today, I think we're all faced with the biggest challenge of our generation, and that's electricity, energy, power. Just to give you a couple of numbers. Global electricity consumption per head has grown over 50% in the last 30 years. And how comes? Well, let's go back a bit in time and let me share some personal experience with you. When I grew up, somewhere in the last century, electricity was used for lighting and a couple of other devices next to that. And the amount of power outlets in the houses was fairly limited. And I don't recall any rechargeable pieces of equipment. And in the 70s and especially the 80s and 90s, they started to change massively, and more wired appliances came and were introduced, and also the amount of power outlets in the houses grew. And during the last decades, we witnessed even a further transition. A boom in consumer technology, mobile phones, computers, laptops, even the watch we have now on our wrist, it serves as a mini computer. The whole cordless revolution, and it all takes energy, it all takes power. Rechargeable technologies that which were only there in small products, they are now becoming common in larger applications as well. And we see little and bigger motors where we've never seen motors before. From toys to support systems in vehicles, from recliner seats to lifeboats. And now motors also, electric motors start to replace combustion engines, obviously in vehicles, but also for instance in garden tools. And boats and aircrafts, they're just starting. And this is expected all to continue and to accelerate. And a few key drivers for this acceleration is the digitization and the electrification that we see all around us. Data centers, just another number, today use around 1% of global electric energy. Processing, big data analysis, cryptocurrency mining, streaming data, artificial intelligence, and many more. It will take the electricity consumption for information and communication to more than 20% of global electricity demand by 2030, 20%, and of which 7% of this is for data centers alone. So all in all, a huge demand for electricity. And in the big picture, we're even on top of that running out of conventional fuel, which also is harming our planet in the way we're using it at the moment. So this puts a clear challenge for combustion engines in all sizes and applications. And again, increasing the importance of electricity, and with that for power and power conversion. And just to augment a bit further, one of the biggest problems in the world is global warming. In the Paris Agreement in 2016, countries committed to reduce emissions. Many countries have now formally put in the law or committed otherwise to be climate neutral or net zero by 2050. and with further commitments to strengthen those targets. They were recently agreed in Glasgow at the COP26. And to realize this, further acceleration of electrification is expected. And I think we recognize that all around us. Charging poles being established, one after the other. Car manufacturer announces acceleration of their introduction of electric vehicles, and it will make that we will be stepping away gradually, but certainly, from fossil energy sources. And it will allow more use of efficient forms of energy, heat pumps and battery electric vehicles. And it makes again the contribution of power semiconductors more important than ever. So if we now look at this forum, we're all power and semiconductor experts and semiconductor manufacturers. We all have a responsible contribution. Our products and the applications we design are carbon neutral enablers. But how are we going to do that? It's all about how we're going to feed the power hunger challenge. And the first and most intuitive approach for us as engineers is looking for physical and technical performance improvements. And as you're all aware, to reach higher level of performance and efficiency for power conversion, we will need to focus on other solutions than standard silicon. And if you look on the graph on the right, it shows the theoretical physical limits of silicon versus two wide bandgap materials, silicon carbide and gallium nitride. And where silicon has benefited from many years of development, the actual performance of products is also closing in to the theoretical limit. Where the actual performance of silicon carbide and gallium nitride at the moment is such that they are significantly better compared to silicon already, though at cost levels that only make solutions in the high-end area possible. Though at the same time, it clearly opens the door for wide bandgap to play an important role in realizing the challenges of the next decades, knowing we have a whole learning cycle ahead of us. And if we spotlight a specific example, the growth of gallium nitride in the coming years. Here on this graph, you see the expected growth of gallium nitride based on a 2021 report by Yole. This market is now in its early stages, and it will show an exponential growth in the coming years, with more than 70% CAGR until 2026. And it is a good indicator that we will be needing wide bandgap to address our overall power challenge, to use electric power in places where we never saw it before, and to use the available electric power in the most responsible way. Let's have a look. How can we contribute to that challenge? First of all, there are a number of aspects that you need to consider. For each application, you need to look at performance, cost, availability, and of course, reliability. Let's take them one by one. Performance. The fast development and adoption of wide bandgap products is allowed performance levels that were unimaginable a few years ago. And some of the new project requirements, they couldn't even be achieved without wide bandgap performance. And still, there's plenty to do in terms of research and innovation, especially for GaN and SiC, which are not yet near to their theoretical physical limits. On the cost side, if wide bandgap has to contribute to the power challenge, then the cost needs to be addressed. The silicon solutions, they've proven their performance in many different ways, entry level, also higher end, but we're all with accepted cost performance levels. And it suits well at the entry level applications for different power levels in the current requirements. Wide bandgap, on the other hand, they are today mainly meant for advanced applications, where the performance is the key factor. The cost is simply not there yet to allow a wide proliferation. And the cost levels will come down, as I will show later on. Then it's availability. If we really want to make an impact, the semiconductor industry and users of power semiconductors, we need to deal with that other critical factor in the semiconductor world. It's the availability and security of supply. And only then implementation can become widespread. And then reliability. I think reliability encompasses all of the before. It is applicable to product performance, it's applicable to commercial sustainability, and it's applicable to the guarantee of availability. All of these elements need to be reliable, otherwise we cannot use them as contributors for our power challenge. As mentioned, I mentioned several different technologies already, silicon carbide and gallium nitride, but there's an arsenal of technology options available, and there is room for all. You only need to take a look at the agenda of today's event with the mix of technologies to see it's not either or, but it is both and. And each application will have its own sweet spot, and that sweet spot will vary in time. And you should also note that the boundaries, as I draw them here, and I deliberately didn't draw straight lines, but I draw curved lines, they are far from rigid. And the actual boundaries, they depend on the trade-off of performance, cost, and availability for specific applications. And they will be moving. The boundaries will be moving as technology progresses and go down the learning curve. And the fact that silicon is widespread is a result of decades of evolutionary improvements. And GaN and SiC, they will go the same way, with all the R&D work and the investments that are going on at the moment. And power GaN has already proven success in many low power use cases. And it's allowing more compact and better efficiency solutions. And also there, we're pushing the boundary at Nexperia, for instance, for power GaN to even higher power levels, providing solutions from 2 kilowatt up to 250 kilowatt. Yes, 250 kilowatt can be achieved. And at a 650 volt level, we have shown demonstrators, have worked through that together with customers, and these are power levels that are definitely achievable. And also, and there the reliability element comes in, also in this range, the products will be compliant to automotive standards and go beyond the standard quality requirements. So, as mentioned already, with reference to the graph, every bubble is the result of trade-offs in the triangle I showed you before. And the actual choice will depend on balancing performance, cost, and supply on availability for the application at hand. Let's talk about solutions. Power GaN on silicon, and at least the way Nexperia is implementing it, it has a lot of potential. We already demonstrated significant achievements in a short period of time over the past years, but it just shows how fast the wide bandgap technology is developing and spreading in the market. If we look at the topic of performance, in less than 2 years, Nexperia introduced 3 generations of 650 volt GaN FETs. They have high power conversion efficiency, and they've measured like that in several customer applications, not in theory, but really on the bench. And we received a lot of enthusiasm around it, including excellent switching performance, which will translate in the end in a better power density. And over 20 years ago, we developed the industry standard for copper clip FET packaging. And we're bringing that now also to the GaN FETs to further reduce RDS(on) levels. To the topic of cost and supply. Also, this is a great opportunity for GaN technology. GaN on silicon manufacturing requires standard silicon wafers in standard silicon wafer fabs and standard CMOS equipment. And therefore, it's easily scalable and intrinsically cost efficient. And that allows us to match the pace of the scalability of the demand. And given the Nexperia track record of shipping 100 billion units on an annual basis, I think there are ways to also bring that to GaN, such that the needs of automotive and other high-performing applications can be met. And then on reliability, and I want to talk here specifically about the reliability of the product. Nexperia is using a proven, robust cascode architecture. And the quality testing, they go beyond AEC-Q 101. And the devices, they passed already the AEC-Q 101 4 times, and the testing is still ongoing. And the cascode, just to be very clear, the cascode architecture allows a very simple, and with that also a robust way of driving the transistor. And also, last but not least, to give maximum confidence to our customer, we also test the device to failure, as we want to explore and are exploring the physical limits. And I have to tell you, we haven't reached them yet. And I want to reiterate it once more. As an industry, we are at the beginning of a learning cycle, or better, we have decades of improvement opportunities ahead of us, especially for GaN. So if we look at the performance challenge, this is really about the ultimate power density. Target application areas for power GaN, they're all in early development, and they're expected to grow fast in the coming years. For automotive, it's all about electrification. The onboard charger, the DC-DC converter, and the traction inverter are the key applications that are in focus over here. But also in the industrial sector, there's the photovoltaic inverters, their use of power conversion in data centers, in 5G, and in Industry 4.0 in general. They're key application areas where premium power conversion is required, and where also in the years after that, it will proliferate in the more standard power conversion. So altogether, I believe power GaN has a strong value proposition for each of those applications in such a way that the customer can take maximum benefit out of his own designs. Yeah, so let's have a closer look at the scalability. And we largely built the GaN on silicon on existing infrastructure and proven concepts. Existing silicon, existing fabs, existing processes. And they're all based on proven and available technology. Just to go through it, we process standard silicon substrates with proprietary procedures, but to put the gallium nitride onto it. And as a next step, we produce the GaN HEMT devices using standard CMOS equipment in the standard wafer fabs. So therefore, it's intrinsically easy to scale it and support the fast-growing wide bandgap, not only this and next year, but also in the years that will come after that. And it's also intrinsically a good path to 8 and 12-inch substrates. Today already, the GaN fab production is running in 2 fabs, one internal, one external, and with the flexibility to go to further multi-sourcing if that would be needed. And the final step, also important for the scalability, is the assembly and test phase. For the new generation 650-volt GaN FETs, we use the dedicated copper clip package. It's designed for high power applications with great performance, but moreover, for the scalability, it's built on the experience from the LFPAC family, introduced almost 2 decades ago, where we shipped more than 8 billion pieces to date, with a run rate of more than 1 billion pieces a year. And it's this proven and available and widely available technology in the industry that provides a clear path to high volume, high quality, high cost effective, scalable production. So, looking at Nexperia's action plan, and I mentioned a couple of things already on it. How are we meeting the challenges that the power semiconductor world is facing? As I've just highlighted, we're very proud to have developed GaN technology for higher power levels in a relatively short period of time. And GaN will help to improve energy efficiency in various applications where it really matters, such as in automotive. And beyond that, Nexperia is focusing strongly on developing other adjacent technologies to address the power semiconductor market. We started development in SiC. We just announced the first products over there. And we are developing IGBT solutions. And not unimportant, we will not stop in taking further steps to improve the workhorse of power semiconductors, the regular MOSFETs. And apart from this, we use our experience on package technology to develop packages which are optimized for power applications with good impact on inductance, on heat conduction, reliability, as mentioned here, the copper clip packages. Plus, we're setting up new development centers. This year we opened a center in Malaysia and in China, and we'll be opening a center in the USA shortly as well. And apart from technology development, we also work on the angle of supply. The front-end fabs in Hamburg and Manchester are being expanded, and we recently acquired another 200mm fab in Newport. We announced earlier this year the start of production of a 300mm fab to further support the growing demand. and assembly capacity, of course, they will grow together with the front-end capacities to make sure that the assembled products can become available as well. So the best solution for customer need or application depends on balancing different aspects such as performance, cost and supply, and we think Nexperia is ticking the boxes in all three of them. So I've explained how I believe that the electrification of our energy systems will continue. That results in an additional huge demand for power semiconductors. We all have a challenge to innovate responsibly, to meet the enormous energy demands while enabling a net zero roadmap. More power, less harm. I've highlighted also a bit about Nexperia's considerations and how we plan to address part of this challenge. And I invite you to join us as we face the challenge. And I invite your comments or questions. Thank you very much.